this question 4. Okay, this time we're going to explore the effects of the load changes on synchronous motor. Okay, and this is a motor this time, is using electricity to do some work. The terminal, the nominate voltage is this, and this is the size of the motor. You will not necessarily use all of this capacity, and the power factor is leading in this case, which is, I think it's just for example. The synchronous machine motor has a reactance 2.5 here, and again we ignore this resistor, and there is a fraction losses and core losses, and the shelf is supply a 15 horsepower load, and the motor power factor is 0.8 leading. Okay, sketch the phase diagram of the motor and find the value of IA and IL. Okay, it's a bit different here is you can see here is this side is always BPN, the input power that was for generator. Okay, and you have the mechanical torque goes in, so that's mechanical power, and there's some losses and is converted to this part. Okay, in the previous slice is going this way, the power, the current. Okay, and then after this losses, then you got this P out equals to √3 VL IL cosine theta, real power. Okay, we did this several times, but this time we are looking at a motor. So the motor, the input power is electricity. Okay, that's the √2. The terminal electricity power goes in, and there is a resistor. If there is a resistor, there's a loss, and it's converted to the other part. Okay, and you have a core losses, mechanical losses, and some other losses, and then you outputting a mechanical power. So this is all upside down. Okay, so the output here is the 15 horsepower. That is on the shelf. The mechanical power goes out to do work. So the Pn is this power plus the losses. Okay, Pn is this power plus this 1.5 and 1, so plus a 2.5. This one plus a 2.5, you got this one, 13.69. Okay, and we say this is this one is 0, so we got 0 loss here, and we have a power factor leading for this one. Okay, so we're going to use this Pn because we just talk about this equation divided by √3. So if you move everything over here, then you will get that equation. So the line-to-line current magnitude is the input power divided by √3 line-to-line voltage. Is also phase voltage, the same for delta connection. Power factor, then you got this, well, not sure where this come from, but this is actually the right number for the line current. And we did this so many times. So this is the delta connection. So the current here is the line current. We need to find the phase current here is divided by √3, and because this is a leading, so if it's lagging we always get a negative, so here we got a positive sign because of leading power factor. Okay, so that's the current. Now we always assume the terminal voltage as a reference, so 0, then the current goes this way. So this is a higher voltage, drop, get that one. So this voltage minus drop equal to EA. So EA is equal to that. And then if you plug in the numbers, you got the EA equal to this one. Okay, so that's the part 1. And part 2, we are changing the load, the shelf load, now increased to 30 horsepower. Okay, and then actually this is wrong. So this is the new input power. Okay, the new input power equals to the shelf power. Okay, that's the mechanical power, output power, plus the load. And then that's the new input power. And now the next part, we are using a new equation. Can we just using this Pn equals to root 3 VL IL power factor again? If we can do that, that would be much handy. The answer is no. You can pause and think about why we can't use this one. The answer is we do not know the power factor here. Okay, but we do know the terminal voltage is the voltage from the power supply, right? It's 208. And we also know the EA, the internal voltage, which we calculated from the previous section, and we didn't change the flux, the excitation current or field current, so the EA will kept constant. So we know these two, we know the access, we know everything here, then we can calculate, we know the power as well, the Pn, okay? And the Pn equal to P out, because there's no actually, not Pn, P out, so the power here is the power here, okay? Because we are neglecting this loss. So that's the power conversion. Then we calculate the delta, the power angle. So this is the power angle, which is 23 degrees. And then we can use the Ohm's law. So the IA equals to VT, use a phasor, minus EA, another phasor, divided by the GXS. Okay, then you plug a number in, you got the IA. And the IA is the phase, that's the phase current, and multiply root 3, then you got this line to line current, which is asked for here. Okay, and this IA is have a 15 degree, here is a degree, and we always assume this terminal voltage here got a 0 degree. So the power factor angle, so this angle called a power factor angle, okay? So they're quite similar to that power angle. So the power angle also called a torque angle. Okay, so these are two different. This one is theta and that one is delta. So this angle is 15. So cosine 15 is 0.97. All right, and then you can draw the diagram like that using all the parameters we got. All right, this is what happens when you change load for your synchronous motor, and you can see your EA and EA1 and EA2 with or without the load change is constant. It's in the same circle, on the same circle, because your field current doesn't change. So these has to be the same. You connect it to the same VT, so that will be the same. So the difference is the current. The current phase and the magnitude will change for different loads.